we are talking about various types of transmission line. These are just introduction. You are not supposed to be memorizing all these things. You are just make you aware of things. And then the most important thing, in low frequency, we assume that the circuit length is much smaller than the wavelength. Okay. And high frequency in microwave engineering, when the circuit length is comparable or smaller than the wavelength, then special design techniques is required. Then we went through some of the transmission line effects. I gave you one example, how a resistor at low frequency looks like at high frequency, the model. The low frequency is just a piece of resistor with R. At high frequency, then you have lead inductance. We have lead inductances. And then we have, in addition to the resistor, we have also a charge separation capacitor. Then we have interlead capacitance, which I said is too small, usually can be ignored. Then one student was asking me why we should ignore. Usually this capacitance, usually the CB is too small. If the CB is too small, then we went and calculated the corresponding impedance. Impedance is very large. So if this impedance is large, literally no current flowing through here. So it can be considered as open circuit. So later on, you can look at this video. Then I show you how that resistor model, resistor high frequency model, high frequency model for resistor. Then we derived the input impedance. And then from there, we try to plot the impedance response at various range of frequencies. First, we looked at the lower frequency range, and it's still a resistor with no frequency dependence. The frequency is not affecting it. But as the frequency increases, suddenly it dips, and then it stops. That's when the parasitics are fighting each other. The parasitics due to inductance, inductive parasitics, and capacitive parasitics form inductive impedance and capacitive impedance. When they equal each other, they cancel. And at this point, the circuit is purely resistive. Then after this frequency, the inductive reactance take over. So I say it behaves like a resistance here, and then at this space, a resistor behaves like a resistor at lower range of frequency, and slightly higher range of frequency, it behaves like a capacitor, and still at much higher range of frequencies, it behaves like an inductor. So these are the things that you have to watch out for. Then let's say if you are an engineer and you bought this resistor for 200 ohms, okay, then you're trying to design at this frequency. You are expecting the resistance to be 200 ohms, right? You're trying to design something for 200 ohms. Then suddenly you're not aware of this model. Let's say you end up designing at this area accidentally, or you ended up designing at this area accidentally, and it's not 200 anymore. It can be like for example, at point 2, at this point, the resistance can be 50 ohms. At this point, the resistance can be 600 ohms. That means it's going to be a total disaster. Say if we put you as a rocket engineer, and then the rocket is going to plunge into the ocean. Okay, so these are the things. And I think I drew this not quite correctly. It's supposed to be it's supposed to be like this, right? Asymptotic. Then we show you how to show the difference between period and wavelength. And then we calculated the wavelength at low frequency. So from a normal human, know the low frequency as 50 hertz, the power line frequency. And the power line frequency, the wavelength is very long. Someone standing at under the power line, okay, it's a very high voltage power line. I don't know how many kilovolts. Do you know the overhanging power line that's on the interstate? What is the voltage it's carrying? Anybody know? Do anyone know? Okay, when you go to AIMST University, then you see a power line crossing a traffic light, and they put a yellow box there, right? Telling you not to stand there, not to park your car there while you're waiting for the traffic light. Now, why are they doing that?
High voltage, sir.
Maybe.
So what does the high voltage can do if you're waiting there?
Produce radiation, sir.
Huh? Say that again. Produce?
Radiation.
Yes, it's a radiation. There's a radiation coming. There's another thing is going to happen. Radiation, but inside the car, the radiation is, your car is metallic. Maybe it's not affected by the radiation. Radiation, your car is like a metal, so it's shielded, but still, you are vulnerable to the radiation. So, okay, one thing is the radiation. What is the most, another important thing?
I think EMF, sir, electromagnetic force.
Okay, electromagnetic radiation. Yes, electromagnetic compatibility. That's one thing.
In case if the wire falls down to the car, right, the whole car will be electrocuted.
Yeah, that's really a very good idea. But there's another thing, like what you guys mentioned here, the EMF and everything. It can cause capacitive coupling. This is your road is car potential, right? And then because it's high voltage, there's always a capacitor. Okay, this capacitor can discharge on anyone at any time. There's one guy died last time when it was raining and he was standing under the power line and doing something. So when it was raining, the dielectric may have, because of the space between, this is ground, this is maybe positive or negative, swinging, right? Negative, positive, AC. Maybe when it's positive, it can jump. Negative, so this is your dielectric air. So if you look at the capacitance formula, if there's a plate, separated plate, right, you have a separation of plate with the area, and there's a separation D. The capacitance is area, dielectric, the material in between the plates is dielectric. Maybe I'll just draw this, okay, a little more clarity. It's a parallel plate capacitor. although this is more related to power, but I still want to point it out, distance and area, and in between, let's say it's a dielectric. So the dielectric here, so the capacitance is area dielectric divided by epsilon. Epsilon area dielectric divided by the distance squared. Distance squared. So the capacitance can increase if the distance is reduced. This is another way the capacitance can be increased is when you increase the area. Another way capacitance can increase is if you increase the dielectric. So the dielectric was air, but when it was a drizzling, the dielectric is different. And the one guy got somebody got electrocuted and died due to capacitive coupling. So this capacitive coupling happens all the time at high frequency. But usually they don't kill you because they are low voltage. But they can damage, if they are high enough, they can cook something within your body, like a microwave. Okay. Transmission line effect. So transmission line effect, so now you consider AC line. I just call this AC line. AC, say 50 Hertz. When we were analyzing electrical circuits at low frequency, what happens is if you send a signal from here, then it's instantly available here, right? There's no reflection, nothing. Because it's a long wavelength. Long wavelength, we calculated yesterday, the wavelength is 600 kilometers. But now, at microwave, the wavelength is comparable to the length of the circuit. So this is the length of the circuit. Now you can see the wavelength is much smaller. Let's say it's smaller than the length of the circuit, then you're going to have a phase delay. This when this phase delay can cause problems. Signals are arriving late, reflection, and all these. Some of the effects we talk about now, one of them is a skin effect. We talked about this earlier. At low frequencies, all the charges will flow across the conductor. However, at high frequencies, what happens is the charges are pushed to the surface. Current is the rate of flow of charges, right? I is dq dt. So all these charges are flowing on the surface now. So that means same amount of charges flowing in a smaller area. So that is going to increase the resistance, and that's called skin effect. So these are the another thing. These are the bad things. There are also good things about. We also can make a good opportunity of this transmission line effect. See, one of the thing is if you want to create a resonant circuit, like for example, we looked at the series resonant circuit where at high frequency, the circuit at certain frequency This is called the resonant frequency. The circuit can be shorted. So it can be used for some beneficial purpose. Maybe shorting this to ground. You want to ground something. Maybe you want to ground the transistor. You have a transistor here, and then first it's open circuit, and then at certain frequency you want to connect this to the ground so the transistor can flow. Right? Just like a remote controller, when you press, you're going to send a frequency that resonate at that particular frequency and close the switch. Similarly, you also can have a parallel resonant circuit that can open a switch. We went through this earlier. You guys, please go ahead and watch the video. So let's now look at a little more in detail about microstrip. I remember you guys, we have done some design work involving microstrip circuit, right? So, but you really don't know, yes, but we don't know. So now we formally introduce the microstrip line, transmission line, microstrip transmission line. Microstrip Microstrip's transmission line. Transmission line, sometimes lazy people write as TL. Since I'm also lazy, so I write TL. So it has a dielectric slab. Substrate. Slab, not slab, slab. Signal trace. We will draw this in a second. I'm just writing this down. Then the most important components. And then you will have a ground plane. Generally, try to do a 3D drawing here. So this is a ground plane. Ground plane means it's not really safety ground or something. It's a return, common ground, common return, common ground where all signals return, common ground. And then this is the dielectric material, and then you have a signal trace here. Signal trace. Is this looks familiar to you guys? Epsilon R is a relative dielectric. Usually people try to use a low loss dielectric. Dielectric slab or substrate. And then also note when you buy this board to before you can fabricate the microstrip, usually you buy, the board will have metal bonded on both sides. The last time one student bought the metal bonded on one side, and then I asked him, why did he do that? He said he is going to try to experiment and see if it's going to work. Traces pattern formed by etching. Formed by etching. Etching, we at AIMST University, we have wet etching. It is necessary when you design the microstrip line, necessary to provide, just like any other circuit, electrical circuit, it is necessary to provide a return path. But in microwave, it must be a low impedance return path. Low impedance return path. So like, in ordinary circuit, in ordinary means AC. In AC circuit, you have a signal traveling, and then it's going through a resistor, right? And then you will have it return, right? Then you usually put the symbol here showing that's a common ground for everything to return. Say if you have another load here, when the current also, all current returning here, current will go and return to the same common point. So we call this common ground. Current will return common. Okay, if you have safety ground, that's something else. You have another wire that's connected to the ground, that's a different thing. So if you have a refrigerator, and then if you want to ground the body, then you have a different safety ground. So all currents return. But in RF microwave, the return, we also have return in RF microwave and MW. We will also have returns. Without return, no energy flows through. Let's say you have a similar circuit, a similar load. So of course, all the currents have to return. And then you also have a common ground. But you must understand, like what we talked about yesterday, when you returning to this ground, you're going to have a wire connect to the return, right, sometimes. And this return will have some inductance. At low frequency, J omega, when omega at low frequency, omega is 0. It doesn't matter, right? But at high frequency, when omega is high, then J omega L then the impedance J omega L will go up. that means you're not going to have a low impedance grounding. Let's say this is your eyeball looking inside here, mean eyes. Okay, then I'm drawing that view. I'm just exaggerating the thickness of the copper. Okay, let me use brown color so that you know this is a copper, right? So this is a copper trace. Usually it's not this thick. It's very thin. Okay, I think that's a good enough. Let's say this is the microstrip. It's a strip. Strip is the copper strip. And then you have a height, which I didn't mention earlier, height, H. In ADS, I think they use D. So this is a strip, and this is the width. And then this is the dielectric material. Okay, let me just draw this line a little bit. So that's and then you also have the thickness of the substrate. The thickness of the sorry, not the substrate, thickness of the thickness of the substrate. T. Thickness is T. Sorry, this is, apologize, not substrate. Thickness of the copper track, copper trace. T is the thickness of the copper trace. T is the thickness. Relative dielectric constant. let's say if you guys want, so our midterm is after 8 weeks, is it? After 8 weeks, right?
Yes, sir.
Okay.
Yes.
I don't know who's going to give the midterm. Let's see. Well, let's see how age, substrate, thickness of the substrate. W, the width of the strip. This is also same thing, you know, strip of the strip or trace. So in AC, when you design the low frequency circuit, you don't really bother about this thickness, width, dielectric, and all this very much, right? Right or not? But things changes at high frequency. All these things must be carefully designed. All these things must be carefully designed because your voltage cross-sectional geometry, W, H of the substrate, so define the ratio, of the voltage. Somebody got the mic on, please turn it off. Current signals traveling. Okay, instead of define the ratio of voltage and current signals traveling along the microstrip line. The ratio is called the characteristics impedance. Impedance of the line. Okay, if this is the line, for example, So let's say the current is traveling, and there's also voltage. Okay, let's call this voltage, current, and current, you know. So the impedance, the characteristics impedance is defined to be the voltage divided by the current. Call this a Z0, characteristics impedance Z0. It's kind of a divided by voltage divided by current, and it must be consistent. This is a 50 ohms line. Let's say we are designing a 50 ohms line, then it must be 50 ohms everywhere. Let's say the signal is traveling, it's 50 ohms, we design for 50 ohms, and then suddenly impedance change here, let's say to 70 ohms. And then therefore it is, there's going to be a reflection here. There's going to be a reflection. This is called gamma, the reflection coefficient. Reflection coefficient. So this is the problem with high frequency design. Last time you guys have used the line calculator in the areas to design your transmission line, remember? The transmission line, for example, from POSA, the characteristics impedance Z0 is 60 over the square root of epsilon E. Epsilon E is the effective dielectric constant. We'll talk about that later. Natural log of 8D divided by W plus W over 4D. This is the equation to calculate the characteristics impedance of a transmission line. You know, this is a microstrip transmission line in this case. Okay, you can see the D. A D is same as the H. Is the D is the same as the H. That maybe I'll just replace this with H. If you go back to this diagram, you know what is H and what is W, right? So the characteristics impedance is determined by this geometry. The W, especially once you bought this, once you buy the board, the height is going to be fixed. However, the W can change. You can design the W to acquire the desired characteristics impedance. If W over D or W over D less than 1, okay, you use this formula. But if this W over D is more equals to 1 or more, then you use this formula. But I'm not going to be asking you to be using all this formula. Maybe there'll be a small example to show you. One small example. The ADS will do everything for you, but as an engineer, you must know where they're coming from. The origin. You don't want to be a push button engineer. As an engineer, you order the substrate. It is some particular substrate, and then you already design for that substrate. The substrate with particular age. But after design, then you see it's not meeting your design spec. Then you go and analyze and see the vendors supply the wrong thickness. The vendors supply the wrong thickness. And then maybe the vendors supply the wrong dielectric. So that's why you, as an engineer, you should have some idea about these things. Have you guys seen this formula before in other classes? Hello, guys. Have you all seen this formula before? Just say yes or no. You know, it's very easy. I'm not going to beat you.
No, sir.
Okay. No. Who has seen? Nobody. Okay. So this is the characteristics impedance. As you can see clearly, the characteristics impedance dependent is geometry. Geometry, in this case, WH. See the W, H, this is a geometry. Once you buy the board, you cannot change H, you know, but you can change the W. Because W is what you're going to H, right? The W is this. The thickness from here to here is W. This is, you can etch, design and etch. This you cannot change. Once you buy that, you cannot change. So characteristics impedance, this term, when you go to the ADS, and then there's also one thing called tangent loss, right? Tangent loss. In ADS, the line calculator, you can see there's a place to enter tangent loss, right? Something like this, tangent loss. And then the thickness like this thickness here, usually is very small. All these values are very small. Sometimes you enter them or you don't enter them. It doesn't make much difference. But W, definitely W is going to make a big change in your design. And H also, and the dielectric material. So these are the very important things to keep your eye on: W, H, and the dielectric, relative dielectric constant. Any questions, students?
So far, no, sir.
So far, fine, right? Good.
Yes, sir. So far, fine, sir.
Microstrip line. A microstrip line. Most widely used. Used interconnect. At radio frequency, at RF. I just put at RF and microwave frequencies. So yeah, let me show you some of this microstrip board. Okay, when you come to microstrip, and this is the, you guys have seen this before. So this is the SMA connector. Okay, this is some kind of a chip, I think. The middle So the thing to note here is you can see when you solder, maybe one of them is the input, one of them is the output. Where you can see, please take a note at this. And note this. Looks like a bad soldering, you see. But that's how, there's a transition there. There's a transition. The pin is connected to the microstrip board. Signal is transferred from the pin to the microstrip. There is definitely a modeling is required. So you can see all these holes are the vias. These are the like the vias. The vias connects the top ground. These are all ground, I think. These are all ground. It's connecting the ground, top ground to the bottom ground plane to give solid grounding. But look at this. The solder is solder. You know, see how you solder the body. So solder the body solidly to the ground. This is not. This is the. All these things are ground. You know, all these are ground. This is the only one that's carrying the signal, the current. The pin carries the current. So this is, I think this must have been done by using NC's electromagnetics 3D. In NC's, I think you can actually draw this and simulate. Coax signal coming in, as you can see right here, it's transferring from the pin transferring to the trace. I use a white color again. Okay. So this is the pin that's bringing in the signal from the outside world. And then this is the trace. But anyway, here he's saying signal out. So I'm sorry, you know. It's saying signal, microstrip signal out, but the arrow is drawing this way. Signal out means it should be drawn the other way. But anyways, don't worry about that. I just wanted to show you the pin and the trace. Guys, can see this? Are you all still live online?
Yes, live, sir.
Yes,
Yes,
sir.
sir. Yes, sir.
So again, you see the top view. So when you want to solder in RF microwave frequency, you have to be very careful. Remember, we told you earlier that at high frequency, signals travel on the surface, right? So the surface must be very smooth. See, this is a very bad pigeon drop kind of soldering. This is what you call pigeon drop. Soldering is not smooth at all. So this can is some kind of a, if it's a dry solder, then you're going to have some stray capacitance, some connection problem there. So the body must be strongly connected like this. But in this case, most of the time when we did our fabrication in the lab, we don't have the ground plane on the top, right? We only had the bottom ground plane. But they have ground plane on top also, which is much better. And then they use these vias to connect the top ground plane to the bottom ground plane. Because as I told you earlier, the ground return must have very low impedance, must have a very low impedance return. So to make the ground equal potential, let's say you have a ground, you have a device here. For example, you have a device here, and then you have a device here. and this is grounded here, and this is grounded here. If they don't have a very good common ground, if they don't have a very good common ground, then they're going to have some kind of voltage drop across here. They're going to have some kind of resistance, voltage drop. If the grounding is not solidly 0 here, maybe it's 0.5, not solid grounding, but here it may be 0. So the voltage difference, maybe here is 0.5, on this side is 0. So that's going to create ground current, maybe not exactly 0.01. They're going to generate ground current, noise, and all that. So that's why in RF microwave, you want to have a good grounding. And this is also just some pictures. Okay, when you put them all together, you see there's a lot of things inside here, splitter, couplers. That's the last time on. So whatever we have studied so far, we're going to use all that information. Given the microstrip transmission line below, the length is 100 cm, width is 5 mm, height is 2 mm, the relative dielectric constant is 2, and then fringing fields can be approximated by using the effective conductor width. Okay, fringing fields. What is a fringing fields? If you look, okay, this is your trace. Use brown for trace. So this is the okay. For now, let's delete this. I just wanted to show you the fringing fields. You're looking into eyeballs, looking into here. It's a ground plane. This electric field always emanating from the trace to the ground. I'm not drawing this very accurately, but give you guys some idea. Okay, that's electric field, E. And then magnetic field. Magnetic field is going to circle around magnetic field is going to circle around the conductor. I don't know which way it's going to go to, but I just put an arrow for now So this is magnetic field. Magnetic field, we call this H, right? H. So this is the field. So now you see, this is a substrate, right? Epsilon. That's a substrate. Now we can see very clearly the fields are also outside the substrate, outside here in the space, epsilon naught. To the substrate inside, if you can keep all the field contained in the substrate, that is better. There's no radiation. And all the energy is inside the substrate. But now some energy is leaking out to the air and it also can radiate. So the dielectric constant in this case consists of two. Epsilon r. Now the field is in two places. It is also inside the substrate and is also inside the substrate and is also outside the substrate. Therefore, we're going to have an effective dielectric. Effective dielectric. When you have an effective dielectric, there's a formula for that. If you have an effective dielectric, that means you also have an effective width. Excuse me. If you want to just effective dielectric formula for effective dielectric is epsilon r plus 1 divided by 2 plus epsilon r minus 1 divided by 2, 1 over 1 plus 12 d over w. So usually, if you want to use this, we don't want to use, but this is given to you. In this case, we can just simply use this. Effective dielectric constant is going to give you effective dielectric width. So when we do simulation, all these things are taken care of the software. But when you do end calculation, we have to look into these things. Are you guys are still around?
Yes, sir.